Well, we'll go over a Latma diagram, and a Latma diagram is simply a diagram of an element that gives us the cell potentials of that element. And so when you have ion 3 plus converting to ion 2 plus, and then ion 2 plus converting into ion metal. So you see that the cell potential for ion 3 plus to convert to ion 2 plus is the cell potential given there is positive 0.771 volts. The cell potential given here is negative 0.44 volts. That means if, let's now relate ion 3 plus first to ion 2 plus. So there should be a cell potential here. Now such a thing which we see like this is what we call as a Latma diagram. What is relating cell potentials of a given element. Alright. Now, how do we find the cell potential at that point? What we do is we are going to relate the standard free energies for each step. The reason is simple. Electrons are not the same which are involved at all these stages. So when ion 3 plus wants to convert to ion 2 plus, it has to gain 1 electron, and then it is going to go into ion 2 plus. And then when ion 2 plus is to go to ion, has to gain 2 electrons. Now when ion 3 plus itself wants to go direct into ion, it gains 3 electrons. And so we need to calculate the free energy for this stage alone, the free stage for this stage alone, and then those free energies, the sum of them will give us now the sum of the free energy for this, and then we can now deduce the cell potential. So let's find the value there. Find E cell, which we can see here, the standard cell potential for ion 3 plus to convert to ion 2 plus. So what to do is, let's first find delta G at this point. Delta G1, delta G is the standard free energy, and that is given by negative N Fe. Okay. So that value, now we are going to go on and substitute the values of N, F, and also E, the cell potential for the stage that we are talking about. Now, the number of electrons involved at the first stage, we can see that only 1 electron has been involved here. So we're going to put a 1. And then F, for F we can just use F for a reason. That is because at the end of it, or this F, Faraday's constant, is going to cancel out. If we want, we can substitute the value of the Faraday's constant, that is 96,485. So it's not necessary to substitute. It's just fine. We can just go direct. Now the cell potential for this stage we've seen is positive 0.771. So if we multiply this, we're going to get negative 0.771 F. So that is standard free energy for the first step. Now let's find the standard free energy for this step, and that is going to give us what? Okay, the formula still remains the same. That is negative NFE. And so where there is N, now for the second step, we can see that 2 electrons have been involved. So where there is N, we are going to put 2. And then times F. Then the cell potential we can see is there, negative 0.44. Now if we multiply 2 by F by negative 0.44, we're going to get a positive 0.88 F. So for us to get the free energy for this reaction, it will be a sum of those two. So free energy for the reaction here is going to be equal to free energy for the first step and then free energy for the second step. Well, at this point what we can do is we'll just go on and say the free energy for the first step gave us negative 0.771 F. For the second step has given us positive 0.88 F. So if we sum these, we're going to get 0.109 F. Now the question is find E cell and not free energy. But we know that if we have free energy is given by negative NFE. So free energy found to be 0.109, and then minus, okay, that is a negative. The number of electrons direct here involved is 3 electrons, so we're going to substitute 3. Now let's not substitute the value for F, let's just write F and then we write E. And so we're going to divide by negative 3F on both sides. So this will cancel with this, and so what will remain is just E cell at this point. So that will give us E cell. The reduction potential will be, anyway, this F and the F here, this is coming from 0.109 F. So I've just written 0.109. There's an F there. So that F and this F cancels out. Now negative 3 into that number, that is going to give negative 0.0363 volts. So that would be the cell potential for the direct process then. Now let's look at another example just to make sure that we understand. So let's say we've been given a process. We have got this compound here. It goes into that, and this also goes into this compound, and then this goes into this compound. This also goes into that one. So we have been also given the reduction potentials or standard cell potentials. Here it is positive 0.90 volts. This is positive 2.10 volts. This is positive 0.45 volts. And then the value there is positive 1.54 volts. Okay. Now look at, we have got a process phase from this point. It can go to here. Okay, let me now just write it direct. We want to find the cell potential that is missing. Let's find this cell potential here. So anything can be missing, and you can be able to calculate just using standard free energies. We can even calculate the direct cell potential from there up to the end at that point. Now let's find the missing cell potential, which is at this point. Now how are we able to calculate that missing cell potential? So we need to break this reaction going into this, and then break this going into that, and then we work with those then, which will be remaining with. So we have got MnO4 minus going into HMnO4 minus. Now we need to understand how many electrons are involved in this reaction. Well, to tell how many electrons are involved, we need first to balance something here. We can see that this portion has got 4 electrons, even that portion has got 4 electrons, but we have got hydrogen here. We don't have any hydrogen that side. Now to balance that hydrogen, we are going to add an hydrogen ion. So that will be H plus added to that one. Now we need to determine what is the total oxidation states of all these compounds on the reactant and on the product. This compound here, the hydrogen ions, oxidation state is positive 1. As you see, it is positively charged. This compound is negative 1. As you see, it has got a negative charge. And this is supposed to produce this portion, the whole of this compound, we can see its charge there, a negative 1. And so this is giving us 0 to negative 1. Now there's a side which we need to add electrons to. To the side where you add the electrons is the side which has a more positive cell potential. I mean a more positive value. Not cell potential at this point, just a value. So in other words, what we are saying, what number should we remove from 0 for us to get a negative 1? We know it's a 1. 1 minus, I mean 0 minus 1 is going to be equal to negative 1. So putting a negative 1 there is the same as adding an electron. So this is telling us on the part of the reactance we are going to add 1 electron. So this will be plus 1 electron here. Okay. So we know the cell potential for that process, it is already there. And then we need also to go to the next process from here up to here. And so we are talking of H MnO4 minus, and that is going to MnO2. Now looking at what we have at this point, we have got 4 oxygens here. We only have 2 oxygens here. The first thing that we want to do is to balance the oxygens. And how do we balance those oxygens? We can see that this side has 2 more oxygens as compared to this side. So we're going to add 2 water molecules this side. Okay, like that. Now when we add 2 water molecules, water molecules like that. If we add 2 water molecules, we can see that we've introduced 4 hydrogens. So to balance those 4 hydrogens, we only have 1 hydrogen here. We need to add 3 more hydrogens. Now the hydrogens we add are in forms of ions. So 3 hydrogen ions. Well, let's now see the oxidation numbers on both sides. We have got a positive 1, but there are the 3 of them, as you can see by that. So positive 3. And then you've got this compound which has got a negative 1 charge. And that is producing, on this side, there's nothing that is charged. All of them are 0. Okay. There's a 0 oxidation number there, or charge. 3 minus 1 is a positive 2. And that is going to 0. So the question is, what number can we remove from 2 to get a 0? That is, of course, a 2. So that means we need to add 2 electrons on the part of the reactants again. So on the reactants, we are going to add 2 electrons. So it will be plus 2 electrons there. Now after doing that, we can go on and find the standard free energies for the reaction, since we know now the electrons which are involved. For the first stage, standard free energy is going to be given by negative NF and the cell potential at that stage. So that will be negative, number of electrons involved is 1, so F will just write it the way it is, and then the cell potential we are getting is that for the process, that is positive 0.90, and so that is giving us negative 0.90 F. For the next stage here, find its free energy, and that will be equal to negative NFE, and that is equal to negative, how many electrons are involved? 2 electrons. That is going to give us 2. For F, we don't need to substitute anything, and then we substitute the cell potential. The cell potential for that process is that, which is positive 2.10. So if we perform multiplication at that point, what we are going to find is, let me go on and multiply. So that is 2 times 2.1. That is a 4.2. It's going to be negative 4.20 F. Okay. Now to get the standard free energy for the reaction from this point up to that point, we need to add these free energies. So say free energy for the reaction we are concerned about will be negative 0.90 F plus negative, anyway, to just be negative 4.20 F. And what we are going to find there is, that is going to give us a negative 5.10 F. Now if from here up to here 1 electron is involved, from here to here 2 electrons, that means direct from there to there it is 3 electrons involved. So go on and find the cell potential which is missing at that point. And so that is given by delta G is given by negative NFE. And so what we can see there is delta G, we found the value negative 5.10 F, and then we have got negative number of electrons for the direct process. For this one we've seen is 3 electrons, and then FE, so we divide by negative 3F, and then this side by negative 3F, and so this will cancel with that, F is going to cancel with that F, so E standard for the cell is going to give us negative 3 into that number to be positive, so the value is going to be positive 1.70 volts. So that will be it. Now Latimer diagrams are very important because they helps us with something. So consider this: when you have a process like, let's say we have got this iron sulfate, and then it is producing some electrons. Well, it gives us iron 2 plus, and then we are saying this iron 2 plus can give us now iron like that. Now the question can be, is this going to disproportionate? Will it go for, so disproportionating is going to tell us, is it really going to gain those electrons, this thing, for it to go to the next thing there? Now that has to do with the cell potentials which are here and here. Now say you have got a cell potential of positive 1.9. Anyway, that is not the cell potential. Say that is the one, and then say the cell potential here is negative. Let me use positive 0. Let's say 5 volts. Now will this disproportionate? So will it go into that? Now that has to do with what you have at this point. Well, what will determine whether it is going to disproportionate is the cell potentials, these two. Okay, so if the cell potential that you can see here, let's call this as the left and this as the right. So a species only has a tendency to disproportionate into its two neighbors if the reduction potential on the right, okay, in a Latimer diagram is higher than the one which is on the left. So because this value we can see here is smaller than this value which we can see, this will not disproportionate unless if this value was bigger, then that would have gone like that. Otherwise it might go in the opposite direction.